Hello, welcome back. We have studied what happens to a harmonic oscillator, being alone or in the presence of friction or under external periodic forcing. Now, let's now couple two harmonic oscillators. In the case of the simple harmonic oscillator, we had a differential equation as x2 dots plus omega squared times x equal to 0. If we have two coupled simple harmonic oscillators, this could be a single mass attached to two springs. Here, the restoring force will depend not only on the displacement of the particle against the rest position from one spring, but also on the displacement of the particle against the rest position from the second spring. Let me write a simple example for this. Consider the coupled differential equations as 2x2 dots plus omega squared 5x minus 3y equal to 0 and 2y2 dots plus omega squared 5y minus 3x equal to 0. We want to find the equations of motion for x of t and y of t. To do that, I'll add both equations first. And I'll subtract the second from the first, then now I have two differential equations that sound very familiar. These two equations have the solutions for x plus y and x minus y. From these results, we can write the equation of motion for x and for y. Look at these equations. The motion is not that of a simple harmonic oscillator. It is a periodic motion, yes, but a bit more complicated than the simple harmonic motion. But if we look at the combined variables x plus y and x minus y, these two new variables do follow a simple harmonic motion. And there is a lot we know now about the simple harmonic motion. Let's show another simple example. Yes, I know I'm solving the simple examples here, and the complicated ones will be left for you to do as homework, but keep in mind that
the universe generally fails to be a fairy tale.
Consider two equal masses m attached to three springs of equal recovery constant x. We will call x1 to the position of the left particle and x2 to the position of the second particle. At rest, x1 is 0 and x2 is 0. So if either x1 or x2 are non-zero, then there are forces acting on the masses. I want to write Newton's second law for both particles. The force acting on particle 1, the forces are from spring 1 and from spring 2, and the forces acting on particle 2 are from spring 2 and spring 3. The force of spring 1 on particle 1 is minus kx1. The force of spring 2 on particle 1 will point in the opposite direction as the previous one, and is k times the elongation of spring 2. This spring 2 has been stretched or compressed an amount x2 minus x1. So the force on particle 1 due to a spring 2 will be k x2 minus x1. If x2 is greater than x1, the force points right. If x1 is greater than x2, this contribution changes sign and the force points left. So far, so good. Now let's write the forces on particle 2. The force from spring 3 will be minus kx2, and the force of spring 2 on particle 2 will, following the same reasoning as before, it is the stretched or compressed amount of spring 2 that matters. This force is minus kx2 minus x1. If x2 is greater than x1, then spring 2 is stretched. This term is negative and points left. If x1 is greater than x2, then the spring is compressed. This term is positive and points to the right. Good. Let's now write the differential equations. For particle 1, the sum of the forces is equal to m times the acceleration of particle 1. So x1 2 dots equal to minus 2 kx1 plus kx2. I'm going to define, as usual, omega squared as k over m, and rewrite this. And the same for particle 2. Here we have again two coupled differential equations. I'm going to add them first and subtract them later. These look very familiar, right? Our very old friend, the simple harmonic oscillator. So we have that these new variables x1 plus x2 and x1 minus x2 again behave as simple harmonic oscillators. This combination of variables are called the normal coordinates of the system. They both oscillate with just one frequency each. Be aware that their frequencies are not the same. So let's now go and solve this system of equations to find the equations of motion for the actuals x1 and x2. These are a combination of two frequencies overimposed. We built x1 and x2 out of a linear combination of the normal variables, the normal modes. The first normal mode has frequency omega, and both particles positions are added, so imagine the whole system oscillating at omega. Both particles move right and left at unison with omega. The atom motion has frequency square root of 3 omega, and the positions are subtracted, so this atom motion would have both particles moving against each other, out of phase, one moving to the right while the other is moving to the left, with a square root of 3 times omega. Now, think about the many physical systems that we can describe as oscillators, and how they can couple themselves. Well, isn't it fascinating the power of the harmonic oscillator? May the science be with you.